The topic for today is demystifying 5G, numerology, and initial access concept. Let's dive into the agenda right away. I would like to start with a short introduction and recap on 5G. I call it Quo Vadis 5G. We look at the status of 5G and R and 3GPP from a high-level perspective. Then we go into the details about the numerology and initial access concept. We include a short demonstration into this webinar. And then, of course, we conclude with a summary and conclusion towards the end. So, Quo Vadis 5G. If we take a look at any given 5G presentation that you have may seen, this is my slide to trying to explain to you what 5G is. From our perspective, it's a paradigm shift. As you can see, compared to the existing generations of wireless communication, wireless technologies. Initially, we had 1G, 2G, where we had to transition from analog to digital, as we all know. And the killer application in 2G was, of course, short message services or texting. With the success of the internet, the third generation of mobile communications was introduced around the millennium, around 2000, 2001, trying to increase the possible data rates and making the mobile internet reality. That worked more or less acceptable. But what all these generations had in common is that basically there was a technology framework being defined, and then the industry and the markets tried to find a killer application for it. With 4G, we changed that. So if we take a look here, the initial thought was basically, let's do a better technology than 3G, increase the data rates. And the industry came up with long-term evolution, LTE. But then the introduction of smartphones and tablets led to a great success of this technology. The technology was delivering the high data rates and the low latency, and that enabled a lot of applications. And those applications include video streaming and social media, like you can see here by these different bubbles. So that success basically made the operator community believing in this technology and deploying it. And then they came back with requirements to enable the Internet of Things. So requirements like improved link budget, lower power consumption, low-cost devices to enable all these sensor networks as an example. And that led to the definition of a narrowband IoT, which is an technology embedded into the LTE standard, addressing the Internet of Things. And now we can continue this path with 5G as well. Operators bring out the requirements, those requirements being analyzed by the standardization community. And then technology should be developed that fit those requirements. However, there are different use cases and different roadmaps and expectations. And that basically led to industry activities versus standardization activities, which you can see here. So basically, we have leading operators in Korea and in the United States that has two very specific use cases that they want to see addressed with 5G technology. And these two use cases are basically fixed wireless access for Verizon Wireless in the United States, and then 5G trial services to support the Winter Olympic Games that are taking place in February 2018 in Korea. And the operators here, the two operators, Verizon and KT, Korean Telecom, they came up with their own specification based on LTE, and the common ground for both operators were the utilization of the 28 gigahertz spectrum to access a wider bandwidth and enable higher data rates. However, if we take a look at the standardization community, the standardization community, 3GPP, has to address a triangle of applications with a coming 5G technology. These triangle of application scenarios can be basically grouped in three scenarios. Enhanced mobile broadband, so wider, faster, higher, as usual, for every other technology that has been introduced so far. But then we are addressing also very specific use cases, which are summarized once as a massive machine-type communication, so an extension of the Internet of Things, basically, but then also ultra-reliable, low-latency communications, where examples would be as a scenario, as an application, augmented reality as an example, or autonomous driving. So those all these application scenarios should be addressed by coming standard. And let's take a look at what the status of 5G NR is within 3GPP. So first of all, the standardization timeline or the timeline when these technologies should come out has been accelerated for a second time. This is basically due to the mentioned industry activities that I just described. There's a specific focus on what is called non-standalone mode, which means that the higher frequencies are basically just used as to create a wider data pipe, and an LTE signal is used as an anchor in a licensed band, typically sub 6 gigahertz. So if we take a look at this roadmap that's being shown here on the slide, you basically see that the layer 1, layer 2 specifications should be available by the end of this year, so by December 2017. And the syntax, that means the signaling, information exchange between a device and the network, should be available by March 2018. So it's a clear focus. Other things have been basically made with a lower priority. And to enable this concept, basically, different connectivity options are currently being discussed in the standard and have been put into prioritization. What the operators want to do first, how they want to address 5G NR, how they want to realize 5G NR. And it's basically a phase-wise deployment compared to the already rolled out LTE networks. So these options are 8 in total if you look into the standards. However, not all of them are feasible. I'm plotting here basically option number 2, which is the standalone version. As we have seen in the previous slide, non-standalone is the one to go for. Standalone basically means that all the control and signaling information is being exchanged over the 5G NR carrier. That comes at a later stage, but it is basically summarized as option number 2. If there's an option number 2, there should be an option number 1, of course. Option number 1 is purely legacy LTE as it is deployed already today. So I mentioned 8 options. What are these other options? Let's take a look. Option number 3, basically there are 2 variants of it, 3 and 3A, where you basically see a G node B, which is basically the name for a base station that supports 5G NR. That's basically connected in different ways to the EPC, which is nothing else than the LTE core network. There's a few enhancements that are needed here that, of course, the standardization will take care of. But basically, the priority, the focus is here on the exchange interfaces between the E node B, which is the LTE RAN, and the G node B, which is the 5G NR. As you can see here, summarized by the XXU and XXC interface. U and C as user stands for user data and control information. However, as you can see, the option 3A means basically that the core network connects the user plane also towards the G node B. That's of course dependent on how an operator plans to deploy 5G NR, and it's what their favorite is. The next option is basically then what is summarized as option number 7, where we have interconnection of these RAN networks, LTE RAN, here shown by the E node B, and then the 5G NR RAN by the G node B, connected to the 5G core network. There's a few more options. Option number 4, which was seen feasible, but that is of a lower priority and will come at a later stage. It's all about priorities. A few general administrative information about 5G NR and specification here. The 38 series is basically what captures the technical specifications and technical reports that describe 5G NR. For the release 15, we put a focus on two of the application scenarios of the application triangle, with a particular emphasis on enhanced mobile broadband. And then in a second stage, ultra reliable low latency communications. The frequencies that have been targeted are up to 52.6 gigahertz. That's coming out of the ITU World Radio Conference that happened back in 2015. The current deployments are foreseen basically up to frequencies up to 40 gigahertz. that has been recently allocated by regulators like the Federal Communications Commission in the United States. And a few of those background documents, the technical reports that all these work items are based on, are basically captured in these technical reports. And I just highlight two of them here. Basically, the one that defines the channel model for frequencies above 6 gigahertz, and basically a summary of the scenarios and requirements that should be addressed by a 5G standard. The next two slides are basically the coming 5G specifications. Again, the 38 series. You see here the physical layer descriptions and the MAC protocols, RLC protocols, basically coming out of the working groups RAN 1 and RAN 2. And then on this slide, basically the specification captured by RAN 3 for all the interfaces, and then also RAN 4 from a test procedure, test tolerances point of view for device and base stations. I just want to mention also, even if that's, there's the hype around the millimeter wave frequencies, 5G NR is not just millimeter wave, of course, and wider bandwidth. It has also a sub-6 gigahertz component. That is basically what you clearly can see here summarized in these two tables, where we have frequency bands that will be combined with licensed LTE frequency bands and frequency bands that will come up in the sub-6 gigahertz base, provide access to wider bandwidths. But then also there's a combination of sub-6 gigahertz frequencies and millimeter wave frequencies. So you can pick here your favorite. Of course, the operator communities in the different regions of the world, in Europe, in Asia, and the US, have their favorite bands. And that is basically what we see here on this particular table. Jumping to the next aspect of this webinar was basically taking a look at the 5G NR numerology, and then using that to describe what the initial access concept is gonna look like in 5G NR. So let's take a look. For this reason, I plot here this particular table. I think by now, if you follow the 5G discussions in general and 5G NR in particular, it is understood that we need to work with a subcarrier scaling here, that based on a certain formula here, a base frequency F0, which has been decided to be 15 kilohertz, like the subcarrier spacing is in LTE, and the scaling factor exponential to the power of n. That leads to these subcarrier spacings, the different ones that being shown here in the table, 15, 30, 60, 120, 240, and 480 kilohertz, of course, leading to a different symbol length. Cyclic prefix is currently still being discussed. However, a few decisions have been made. For instance, for the experts on the physical layer from LTE, we know there's a normal and extended cyclic prefix in LTE, even if their only normal cyclic prefix has been deployed by network operators worldwide. There's a similar thing coming with 5G NR, but an extended cyclic prefix is only supported for 60 kilohertz subcarrier spacing, and that's specifically targeting the URLLC application scenario. It has also been decided that usually a slot being defined as 0.5 millisecond duration for 15 kilohertz subcarrier spacing, like is in LTE. We don't assign a time unit to the slot anymore. It's more defined by a symbol, as we have different subcarrier spacing, and so a different number of symbols would form that time slot. In the case, as you can see here plotted in the table, for up to 60 kilohertz, it could be either 7 or 14 symbols per slot. And for above 60 kilohertz, it would be definitely 14 symbols per slot. Also, we have a subframe duration of 1 millisecond. The symbol needs to align at 1 millisecond, which is an important. But then most interesting question is, of course, what is the maximum bandwidth that a carrier has to support? There's different views in that from a RAN 1 physical layer perspective, but then also from a RAN 4 perspective. As you can see in the table, the minimum bandwidth for sub-6 gigahertz is 5 megahertz. The maximum bandwidth is 100 megahertz. And for above 6 gigahertz, we're working here with 50 megahertz minimum and 400 megahertz maximum. That means if we want to utilize, for instance, a total bandwidth of 1 gigahertz or 1.2 gigahertz, that some of these frequency bands are offering. We need to use carrier aggregation and dual connectivity. Also, there's a view on that in RAN 1, how many carriers that should be, but also from a RAN 2 perspective, currently being discussed with certain working assumptions. And also a modulation scheme, as you can see here, nothing really fundamentally new. Is also stuff that is being understood from LTE, QPSK 16 QAM, 64 QAM for sub 6 gigahertz, 256 QAM, both in downlink and uplink, but then also in the uplink side, an additional BPSK-based modulation scheme shall be supported. So moving on here, looking at the numerology and in particular in the subcarrier spacing, you see here basically that we have these different subcarrier spacings plotted. As you can see, the 15 kilohertz baseline from LTE for 30 kilohertz, that means I have now 2 symbols in there with 2 cyclic prefixes. 60 kilohertz would mean it would be 4 symbol plus the cyclic prefix and so on. That's the first thing, because we have a 1 millisecond alignment here. But then also for the different frequency bands that are being targeted, the sub 6 gigahertz and the above 6 gigahertz, those subcarrier spacings will be utilized in these different bands. For instance, below 1 gigahertz, been decided that it could be either 15 kilohertz or 30 kilohertz. Between 1 and 6 gigahertz, it could be 15, 30, or 60 kilohertz. And then for the centimeter wave and millimeter wave frequencies, my options are only 60 to 120 kilohertz. So we have seen that there's 240 and 480 kilohertz from a RAN 1 perspective. However, RAN 4 has been decided that 480 kilohertz doesn't give any particular advantage, and 240 kilohertz doesn't give an advantage from a data channel perspective, but eventually from a synchronization signal perspective, which we will discuss a little bit later. However, you see here there's already exclusion from our working group points of view within the standardization bodies, and I put that in here with the different footnotes for you guys studying this presentation a little later. Just a word why there are different subcarrier spacings. If we go up in frequency, then the impact of phase noise becomes more relevant. So we need to work with a wider separation. That's why the wider subcarrier spacings than the 15 kilohertz, but they only make sense at the higher frequencies. And I think with the explanation at which frequency ranges these subcarrier spacings will be used, we could get a common understanding how to play these and where they are used. Okay, so let's move on with this initial understanding to the initial access concept and procedures within 5G NR. The good news is it's very similar to what's being done in LTE today. Usually random access is the device trying to get access to the network. Like in LTE, there will be a contention-based and contention-free procedure. Basically, the device will send a preamble at certain frequency and time occasions. The network will respond with a random access response, and then there will be the first scheduled transmission in the uplink. That's something that's fairly understood from LTE days. The difference here is significant, of course. If that later on should also work on millimeter wave frequencies, then we have to probably work with beamforming, beam management, and that has a certain impact how we standardize these procedures, but the general concept is basically the same. So in order to do all of this, which is currently under heavy discussions within standards, one device has to gain initial synchronization with the network. That's basically happening while listening to the downlink frequencies and acquiring certain synchronization signals and so-called minimum system information. 5G NR is no difference in that matter or compared to LTE. However, there's a few additional things that have been introduced that I want to highlight with you in the next couple of minutes. So the 5G NR synchronization and downlink, as we can see here on the slide, basically is based again on synchronization signals. But these synchronization signals, including the broadcast channel, are mapped to so-called synchronization signal blocks that are then organized in bursts and burst sets. So this was for a long time under discussion. What I plot here in the graph is basically the outcome of the latest RAN1 report from May 2017, where you basically can see the number of SS blocks available is dependent on the frequency, carrier frequency being used. There's 2 or 3 conclusions. Sub 3 gigahertz is basically 4 of those blocks will be available. Between 3 and 6, it's 8. And then between 6 gigahertz and 52.6 gigahertz, it will be 64. It has also to do with the minimum TTI that we're using for the broadcast channel. In LTE is the physical broadcast channel. For NR, we just add a NR in the beginning, so it's an NR-PBCH. And that is, as in LTE, 80 milliseconds, as you can see here. So if we look now what happens to such an SS block, what is in there, we basically have a periodicity when these synchronization bursts occur or burst sets occur. And within these blocks and burst sets, we have the possibility to map these different signals. Signals that are familiar from LTE, there will be a primary synchronization signal, there will be a secondary synchronization signal, and again, there will be also a broadcast channel. The question is, how are these mapped? How many symbols are occupied? And that's basically what we're seeing in this particular slide here. So you see, basically, it has been agreed in the recent meetings that a time division multiplex is used for the synchronization signals and the broadcast channel, that we're using 1 symbol each for the primary and secondary synchronization signal, that the current working assumption is to use 2 symbols for the broadcast channel, and that the subcarrier spacing for those is basically frequency dependent. So if I'm working sub 6 gigahertz, then the subcarrier spacing could be 15 or 30 kilohertz, like I explained earlier. That means also that those signals, synchronization signals, occupy a certain bandwidth. In the 15 or / 30 kilohertz case, the maximum could be 4.32 megahertz or 8.64 megahertz. And above 6 gigahertz, these subcarrier spacings will be 120 kilohertz or 240 kilohertz. And in that case, my synchronization bandwidth, if you allow me that term, could be either 34.56 megahertz or 69.12 megahertz. And that is basically the reason, like shown earlier in that 5G and R numerology table, why we need also the definition of a minimum system bandwidth for 5G and R for sub 6 gigahertz and above 6 gigahertz, which has been then defined by RAN4 to be 5 megahertz and 50 megahertz. So coming back to the mapping, that is not yet decided. So you see here the 4 different options. One thing that has been decided, that the primary synchronization signal is always being transmitted before the secondary synchronization signal. And that leaves me with these 4 options that you can see here. And 3GPP has to down select from these 4 options, which has not yet been done. So let's take a look at a few more details that are being available. You see here some details on the primary synchronization signal. It's basically a frequency domain-based pure BPSK-M sequence that is based on a certain polynomial, as you can see here, with a certain initialization value for the register, and so forth. We have 3 different cyclic shifts. That brings me 3 different sequences, and you see here basically a plot out of a MATLAB environment where we simulated these sequences. What is important is, of course, the correlation behavior. It's the same thing. We correlate here these sequences. You see the autocorrelation function. There's one peak for it. And then you see the cross correlation, like how much they correlate with each other. So very low, as you can see, nearly around 0. So that will enable me to distinguish between the different cell IDs that are being based on the NR primary synchronization signal. Very similar or exactly similar like what it is in LTE. The cell ID is then based on the combination of the primary and secondary synchronization signal. Also, you see here the definition of these SSS sequence, and on the right-hand side, basically a plot in the constellation diagram. You may think like, oh, there's a lot of things already been decided. Well, not for everything. Much more has to be discussed within 3GPP RAN 1, but a few more information is available that we already can work with. So let's take a look at the broadcast channel, what's known there. It will be QPSK modulated. It will carry the master information blocks. So from that high-level definition, basically nothing different than in LTE. However, it's also being discussed how to ensure proper demodulation of this channel, also allowing basically combination of different reception of this channel. So a lot of things being discussed. One example that I highlighted here from one of the contributions towards RAN 1 as a potential discussion point. You see here two alternatives for certain demodulation reference signal embedding into the overall structure. Something is being decided. And on the other hand, also the content has to be decided where, for instance, here on the right-hand side, you see a related document from RAN 1, a liaison statement towards RAN 2, where they basically describe how to use these bits that are available for the broadcast channel and what should be the minimum system information that's being sent on this particular broadcast channel to help the device to continue with the initial access procedure. So basically, what does that mean from our signal generation, signal analysis point of view? A lot of open things in standards right now. So it's a little bit like Lego. Yeah? So you have a lot of building blocks, and they are currently look sometimes a little bit unorganized. But as I've shown you, a few of the informations are already available, so we can basically organize this. But how the house looks later on, that's not known yet. Yeah, what color the house has, how the roof is looking like, all these things. If you allow me this analogy, that's not yet known. So what does it mean from a signal generation and signal analysis point of view? Like I mentioned, you need a very flexible test solution for that. If you want to become an early adopter and start developing components, RF components, test RF components on their behavior, characterize them, and so forth. So to become an early adopter, you need a flexible test solution, and good that there's Rohde and Schwarz, because we provide that to the industry. So let's look at typical test setup for 5G RF parametric measurements up to the 40 gigahertz frequency range. You basically see here our flagship signal generator, the SMW200A, with built-in 2 gigahertz modulation bandwidths up to 40 gigahertz RF frequency. It is the only instrument in the market that allows this. It has a built-in automatic correction for the frequency response of the IQ modulator. It doesn't matter what waveform you play. It doesn't matter at which frequency. It doesn't matter at which power level. It's correcting by itself for that. So that's unseen in the market. And there's a few software options that allow you to already generate today 5G and R signals, including what Verizon Wireless is doing with their specification, but also what 5G and R is looking like. We come to that in a moment. On the analysis side, on our end, that would be the FSW signal and spectrum analyzer that has a built-in analysis bandwidth of 1.2 gigahertz. It's also unmatched in the market and also matches the current frequency band allocations, for instance, that has been made in the United States for the widest maximum bandwidth that these frequency bands support. And then in addition to that, Rohde and Schwarz launched the FSE software that has an option called K96, which allows for OFDM signal analysis. And if I haven't said it, 5G and R will be based on OFDM, so which allows us to use these tools to create waveforms and analyze them, and then use them to characterize RF components as an example and measure their performance in terms of error vector magnitude and so on. So before we get to that, we need to build a waveform. For that, we can use option K114 on a signal generator. Basically, you see here a few screenshots. On the left-hand side, basically, we adopt a numerology that I've just discussed with you and that I presented in the table. In the example here, I use a FFT size of 4096. I decided for a subcarrier spacing of 120 kilohertz. I'm using the defined occupied numbers of subcarrier with 3,300. That leads to a certain sampling frequency and to a certain occupied bandwidth. That is, in my example, 396 megahertz. And so we fitting the maximum bandwidth requirement or defined bandwidth for a component carrier for millimeter wave frequencies. If we take a closer look, further closer look, the left-hand side allows us to span a resource grid in frequency and time. Now we need to allocate these resource elements, and that's basically the two screens that you see on the right-hand side. So taking a closer look here, I'm looking here at a full 1 millisecond subframe that I fill from a symbol perspective with different allocations. So if you look at the green, that would be my data symbols. The subcarriers, the resource elements in these symbols are modulated, for instance, 64 QAM. In the beginning, I have a control channel that is expected to be QPSK modulated, occupies a certain number of symbols. In my example here, it is 2 symbols, which is in line with the current working assumptions in 3GPP RAN 1. And then if you look in the beginning of that particular subframe, in the beginning of that 1 millisecond, first of all, we have a little gap here that represents basically a guard symbol and another symbol that could be used for uplink transmission. So it's more realistic scenario because 5G NR will be a dynamic TDD-based system. But coming back to what I said in the beginning, here also I highlight the synchronization signal block that I discussed earlier. So if I look into a couple more details here, you basically see I'm zoomed into the first 14 symbols of that 1 millisecond. And you see here the first 2 symbols, like I said, I'm using that for a control channel, QPSK modulated. Then I have it surrounded by data. I have my gap that allows for switching the transmitter from receive to uplink. And within that, I have that SSS block. And if I look at my allocation table, then I basically map here my primary synchronization signal that occupies 127 subcarrier. That's defined by 3GPP RAN 1. So does the secondary synchronization signal. And the broadcast channel, as you can see, occupies 288 subcarriers. Now 288 subcarriers with these different subcarrier spacing, 120 kilohertz or 240 kilohertz at millimeter wave frequencies, basically lead to a different occupied bandwidth for the synchronization signal. So there is in the flexibility, and that's why you need to adopt that into a flexible option to create a waveform like that so that you can test for this. If you have a flexible option to generate these signals, then you need also a flexible option to analyze those signals. Rohde and Schwarz signal analysis software is called VSE. VSE stands for Vector Signal Explorer. And for 5G analysis, we just added recently a generic OFDM signal analysis capability that is called option K96. So enough words. Let's take a look at these setups. For the demonstration, I brought you 2 instruments here. The SMW200A vector signal generator on top of the stack here, and on the bottom the FSW vector signal analyzer. So basically what we will be using is 2 options. As I explained, the option K114 to generate a 5G NR signal that is based on a cyclic prefix based OFDM, as explained throughout the webinar. And on the bottom, we will use the FSW to do an IQ capture. We do this at millimeter wave frequencies. I've chosen 28 gigahertz for my example here. And let's take a closer look on the signal generator. For this purpose, I basically go remote desktop into the instrument. You're seeing here the personality, where I basically have baseband functionality, and here the IQ modulator and RF up conversion. The SMW supports frequencies up to 40 gigahertz, and we support an internal modulation bandwidth up to 2 gigahertz wide signal. So more than enough for any of the current discussions around 5G. So let's take a look at the baseband functionality. If I open it up here, you see we can generate a lot of wireless communication standards. In terms of 5G, you see here basically two options. Basically the Verizon 5G technical forum specification, basically an adaptation of LTE. But what I would like to use today to do a 5G, to create a 5G NR signal is basically using the 5G candidates option, which is the option K114 as I mentioned it. So if we click that, we basically enter this functionality. I'm using basically filtered OFDM here as a basis. And as first, we taking a look at the general settings, and then we look into allocation. So general settings is basically giving me the capabilities to define the numerology. As explained throughout the webinar, you define an FFT size, you select or decide for one of the subcarrier spacings. The number of occupied subcarriers is given, and of course dependent on the selected FFT size. You see here the sequence lengths, which I decided on to fill up the 1 millisecond subframe duration. And as explained, a cyclic prefix hasn't been decided yet, but I picked here a combination that is very similar what has been done in LTE, where the first out of 7 OFDM symbols has a longer cyclic prefix than the remaining 6 ones. And as you can see, I can very flexibly configure that here. You see that gives ended up in a certain sampling rate, 491.52 megahertz, and gives me an occupied bandwidth of 396 megahertz. And as I explained, the maximum carrier bandwidth beyond a 6 gigahertz carrier frequency, according to the current discussions in 3GPP, RAN 1 is 400 megahertz. So our signal configuration fulfills all the requirements and current working assumptions. So that is that. The next step would be now to decide for an allocation. If you enter that setup here, you get a user definition where you basically can choose different data sources. You can load data lists, as I have done here in my example for certain user configuration. As the scrambling method is not yet fully specified for 5G NR, I just went to LTE, took the scrambling out of there, and used that as a data list here that's being loaded. You see that here. But the more interesting piece is, of course, the allocation, as you can see here. Basically, I'm using 23 different allocations to span a frequency and time grid or resource grid as you like, and I'm filling that up with certain allocations, defining certain number of subcarriers that are being occupied in a certain number of symbols. There can be offsets, and here you basically see the data sources that I defined earlier. So if you take a look what I did here, basically at the time plan, it becomes much more clear than just looking at the numeric values that I decided on. You basically see here the same example or screenshot that I used in the slides for this webinar. You see basically in the beginning I have 2 symbols marked here in blue over the entire bandwidth that I configure as a control channel, QPSK modulated. So I basically go back into allocation. I see that here, QPSK modulated over the entire bandwidth for 2 symbols. Green, as shown, is basically data, 64 QAM modulated. Then I have a gap here. The gap is basically 1 symbol that I'm using as a guard period. And then this next symbol would be allocated for uplink. But since I'm generating a downlink signal here, which I can use, for instance, for device receiver testing, I, of course, don't populate here any uplink transmission. That's why we see a 2-symbol gap here. And then that is repeated throughout the 112 symbols that are defined, as you can clearly see. And one of the highlights, as I mentioned, is this synchronization signal block in the very beginning that you can see here. I can also zoom in here, as you can see in my time plan, and go down basically, for instance, to 14 symbols that would define a time slot. So it's much more clearer here right now. You see here the 2 symbols, control, data, and then basically 1 symbol being used for the primary synchronization signal and 1 for the secondary, and then 2 symbols for the physical broadcast channel, as I explained earlier. So if I look into the allocations again, then you see here standardized modulation schemes, QPSK 16 for QAM. But as explained, these synchronization signals are specific type of signals. An M sequence for the primary synchronization signal. I showed you the constellation diagram, how it looks like coming out of the MATLAB environment. And what we basically can do here, and that is a unique functionality, you basically can now decide on using, for instance, what we call custom IQ, that allows me basically to export a sequence out of, for instance, MATLAB, write it into a binary file, and then use that as a data list here. And I'm doing that for the two synchronization signals. As you can see in my example, I have a sequence for NR-PBCH, so the primary synchronization signal, and the secondary synchronization signal. And basically what those files are values for I and Q, and I map these then on the allocated resource elements. And if you take a look here, of course, these resource elements in form of subcarriers are here 127, as is currently being assumed as a working assumption in 3GPP 5G NR for synchronization. So that's basically it. My signal is built according to the specification. I create a waveform that is here 1 millisecond long. I had switched that on. So the baseband is generating that. We're giving that to the analog part of the signal generator. It does the IQ modulation, RF up conversion. I'm transmitting that here at 28 gigahertz. I decided for a subcarrier spacing of 120 kilohertz. That is an indication I'm at higher frequencies here. Also the 400 megahertz occupied bandwidth that I'm doing. And then, of course, I'm transmitting at a certain power level. I decided here simply for 0 dBm. And nice, also you see here the peak envelope power being right away displayed for my waveform. So my crest factor within the waveform is about 12.67 dB, which corresponds to what we would expect from an OFDM-based signal. So now I have the waveform. Now I can transmit at the frequency. I could feed that into my receiver. Of course, now that I have done that, I also would like to take a look at the analysis part. For that, I'm using the VSE software, the Vector Signal Explorer software, with its option K96 for OFDM-based signal analysis. But before I can do that, I basically would have to create what we call a configuration file. That's basically loaded into the analysis software so that I can demodulate the signal. Of course, doing that for this signal is a little bit time-consuming, but let's take a quick look here how that would look like. You see here on my screen now the what we call the configuration file wizard. It's basically giving you that constellation diagram, and basically you have to run through different steps, which are very self-explaining. And you do perform certain allocations. And if you take a look at the right-hand side here, you basically see also a time plan. At this point, the carriers, so the frequency axis is here on the x-axis, and time, the symbols are on the y-axis. And as you can see, I allocated my configuration here with the control channel and the sync signals being used as pilot for channel estimation and then proper demodulation of the signal. And then, of course, you see here the green part. That would be my data symbols, which are 64 QAM modulated, as I explained earlier. So if I have these configuration files, which is nothing else than a simple XML file, that's being used and loaded within the VSE software. As you can see here, I loaded that for you. This option has been recently added to the VSE software. You see here all basically the symbol rates, FFT sizes, and so forth. Basically, if I click here, I get into the menu where I have to define all these different settings, or where I can also define capturing time and so forth. Also, you could go through the measurement setup and do this here, burst research, sync and tracking, where you can add a trigger, define for the demodulation side, how to do the synchronization, do a phase and time tracking using pilot and data for channel estimation and so forth. I basically did that here. You see here we're doing a measurement. You see an allocation matrix. You see here pilot, QPSK, NR-PBCCH, which are basically the first two symbols that I explained earlier, QPSK modulated. So you basically find everything in that file as I generated that with the signal generator. And of course, I'm doing my measurements here. You see here EVM. Parametric search, and I can switch, of course, to a lot of different other measurements. You see here the EVM versus carrier measurement. I can switch to symbol side, look at that. I can add these windows if I like, so that I have them all the time available. I just decided here for a few windows just to have a basic overview and do that for you. And simply what I would do, I would just run the button here. In that case, it would perform an IQ capture and then basically take the measurement and update the screen. So just a recap from the demonstration. Again, with option K114, we are basically enabled to generate OFDM-based signals that we could use for 5G and R signal generation. The option is very flexible with the custom IQ feature that I showed you to map the sequences being used for the synchronization signals according to the current discussion in standard allows me to map those sequences to the resource grid, basically to the allocated subcarriers and symbols very easily. And it's custom IQ, so basically it allows me to take any sequence that I have generated in MATLAB and map that to the resource grid. Something that I didn't show you, but which I don't want to forget to highlight is the usage of a transmit filter. Basically very simple. In the SMW and K114 option, I can load a user filter, for instance, generated by using the FIR module that is in MATLAB, basically deciding for FFT size and subcarrier spacing and using that to create a filter and saving these filter coefficients and load that into the signal generator and apply that to my waveform for filtering. So this brings me to the conclusion for today's webinar. I think I showed you that 3GPP has started with the standardization, but also has accelerated the standardization process for 5G and R with the goal to finalize the layer 1 and layer 2 aspects by the end of 2017. The first decision on the physical layer have been made. I summarized them throughout this webinar. In particular, for instance, on the numerology and also on synchronization signals. That allows us to create basically arbitrary waveforms, which we can use to do early testing of RF components, such as a power amplifier, for example, or filter, or a complete front-end module. I think I showed that Rohde and Schwarz is committed to 5G and R, that we have already today flexible test solutions available in terms of signal generation and analysis, and we will continue to enhance them as fast as the standard makes progress. And of course, was a lot of information, and we summarize a lot more information on our website. So if you're interested in anything related to 5G, then please visit rohde-schwarz.com/5G. Thank you so much for your attention.